universal forgery, and committing attacks against revised ROCA, how finalization affects security. This is a paper by Ryonuchi Takeshi, Yosuke Todo, and Tetsu Iwata, and Ryonuchi will present the talk.
Thank you for the introduction. I am Ryunosuke Takeuchi from Nagoya University. Today, I will talk about ROCA and how the choice of finalization affects its security. This research is collaborative work with Yosuke Todo and Tetsu Iwata. First, I will provide an overview of our research. We conducted an analysis of ROCA and non-space AAD designed for beyond 5G and 6G. However, previous research has identified the security vulnerabilities in ROCA. To address these security issues, ROCA has undergone several design revisions by key absorbing during initialization and finalization. However, the latest version of ROCA finalization key was removed without a specific explanation, with raising security concerns. Motivated by these concerns, our research objective is to analyze how the choice of finalization affects the ROCA security. Our contribution can be summarized as follows. We examined the impact of keyed and non-keyed finalization on ROCA security, and we demonstrate that keyed finalization enables key recovery attacks, and we confirmed that non-keyed finalization remains vulnerable to forgery attacks. Lastly, we analyzed committing security in different finalization schemes. Based on these results, security trade-off must be considered to determine the appropriate choice. In this presentation, we focus on key recovery and probe attacks. Okay. So before we analyze lookup, let's briefly review AED. Authenticated encryption provides both privacy and authentication, and the inputs include a key, nonce associated data, and plaintext, while the outputs are ciphertext and tag. AED provides some security properties, confidentiality, integrity, and committing security that have recently gained an attention as an important security issues. ROCA is AES-based AAD proposed by Sakamoto et al., designed for beyond 5G and 6G. The key length is 256 bits and tag length is 128 bits. The initial state generated from the key and nonce and tag is derived from the final state. The encryption process consists of initialization, processing associated data, processing message, and finalization. Rand function updates 8-block internal state by absorbing 2 blocks plaintext. The circlet marked A represents the AES rand function. Next, we will examine the state recovery attacks on ROCA proposed by Hoseyama et al. Under nonce-respecting setting, where the attacker cannot reuse a nonce, the attack complexity is due to the 128. Under nonce misuse setting, where the nonce reuse is allowed, the attack complexity reduces due to the 20. This state recovery attacks directly leads both key recovery and forgery attacks. This is because once the state is recovered, the encryption can compute forward and backwards, allowing direct retrieval the key and tag values. Due to these attacks, ROCA has undergone several design revisions by absorbing key during initialization and finalization. Each modification aims to improve resistance to key recovery and forgery attacks. In our research, we define original ROCA as ROCA v1 and revised version as ROCA v2 to ROCA v4. The latest version, ROCA v4, retains the initialization key, but removes the finalization key. Since the initialization requires a key, the security of finalization key still needs to be considered. Here you can see the structure of ROCA v2 and ROCA v3. State recovery attacks is still possible in orange regions in both versions. However, due to key absorption, the initialization and finalization remains unknown and preventing forgery and key recovery attacks. Additionally, Hoseyamada et al. And Sakamoto et al. Propose a different key position in the finalization phase. In ROCA v2, the key placed in the different blocks than the input data. And in ROCA v3, the key placed in the same block as the input data. To simplify our explanation, we will focus on ROCA v3 in our attack analysis. This is the result of our key recovery attacks. Our key recovery attacks demonstrated that the key absorption during the finalization enables the key recovery attacks. In non-smooth setting, the attack complexity is due to the 128, and the non-respecting setting, the attack complexity is due to the 192. Even if a linearly extended key is used in the finalization phase, the key recovery attacks is still possible with the complexity of 2 to the 208. Next, we will introduce the attack procedures on ROCA v3. We consider ROCA v3 for one round input in non-smooth setting. This attack follows the base attack balancing queries and offline computations. Next, we analyze attack procedure step by step. First, we recover the initial set S0 via the state recovery attacks. This requires 2 to the 20 complexity in non-smooth setting. Next, we examine the relationship between the input and the key in the orange section on the right, as shown in next slide. In ROCA v3, the key and input absorbed in the same block. So, as shown in the figure, the finalization inputs are M0 plus K0 and M1 plus K1, and output is T. So we focus on this input-output tuple. Second step, we set M0 as lowercase m0 and M1 as 0. So we consider the tuple M0 plus K0 and K1 and output T. Query for each 128-bit M0 and store the result in a tag list. After gathering the tag data, we proceed to search for K1. We set M0 plus K0 as 0, M1 as 0, and K1 as lowercase k1, and we consider tuple 0, lowercase k1, and output T prime. We computed tag T prime for each K1 by using offline finalization. Compare T prime with recorded tag T, and when input pair satisfying M0 plus K0, K1 is equal to 0 K1, then T is equal to T prime. So when T is equal to T prime holds, the corresponding M0 K1 is a candidate for secret key pair K0 K1. For every matching candidate pair M0 K1, we perform the verification step. We recompute the initialization by using M0K1 as a key. If the set computed in this way is equal to our previously recovered S0, the candidate pair is confirmed. Thus, we recover the key K0, K1 is M0, K1. With this procedure, key recovery attacks succeed with due to the 128 complexity. Let's discuss a potential countermeasure against key recovery attacks. One possible approach is linear key scheduling. This considers key absorption to the different blocks or incorporating the key to the entire internal set. However, key recovery attacks is still possible with a complexity of 2 to the 208. So our findings show that key absorption placement does not impact key recovery attacks. Next, we talk about committing attacks. Committing attacks aim to find input pairs that produce the same output. We consider the several variations of committing attacks from and CMT1 to CMT4. Flop attacks is the most strongest attacks in these properties. The committing security of Locker has been analyzed. However, previous research has not found any attacks more effective than the generic attacks. This table is the result of our committing attacks. This table shows that no version of Locker is fully secure against committing attacks, and flop attacks can only be performed on schemes without a finalization key. Next, we talk about flop attacks on Locker v4. Flop attacks aim to find input pairs that produce the same output when k is not equal to k prime and n is equal to n prime. So the idea behind this attack is if the internal set after the associated phase is identical, the output CT remains the same. So first, we initialize by using different key k and k prime and obtains internal set S0 and S0 prime. At this stage, S0 and S0 prime are completely different as shown in the colored blocks that indicate the different values. Next, we use associated data phase to align 6 out of 8 internal set blocks. Finally, we neutralize the difference that remains 2 colored blocks. Flop attack is complete. Next, we examined how to align 6 out of 8 internal set blocks. First, we obtain the internal set S0 and S0 prime, and next, we input associated data, and after 4 rounds, we internal set match for 6 out of 8 blocks. Looking at this process, for example, the red bordered blocks S40 can be controlled by adjusting the preceding input A6. It as to set to desired values. So similarly, the white colored blocks is controlled by the corresponding input and align 6 out of 8 internal set blocks. The difference remaining 2 blocks propagate to 3 blocks in the next round. So we aim to cancel out the difference between yellow and blue blocks and blue and orange blocks. Specifically, if we can find a ninth, so that the difference cancel out. The relationship between yellow blue and orange blue can be expressed as follows. So If we can define the difference of S54 as delta x and S53 as delta y, to cancel out the difference, AS round S54 plus AS round S54 plus delta x is equal to delta y must hold. Next, we examine the properties of ASS box. For randomly chosen delta x and delta y, there exists x that satisfying this equation with a probability of approximately 1/2. One block consists of 16 bytes, so the probability of satisfying previous equation is 2 to the minus 16th. Therefore, by repeating this process approximately 2 to the 16 times, we can find A9s that cancel out the difference. Finally, we select common M and encrypting it, we can obtain identical output CT, and probe attacks will succeed with a complexity of 2 to the 16. To conclude, it is believed that key absorption in the finalization phase is preventing inverse forgery, but it became the cause of key recovery attacks. And on the other hand, removing the key does not stop the forgery attacks in non-misuse setting or probe attacks. A stronger finalization process is one possible countermeasure against key recovery attacks. And it is essential to determine which security property to prioritize and make an appropriate choice accordingly. Thank you for your attention.
You have some questions? Yeah, I see no question. So I do have one. In one of your slides, you were talking about doing some linear function in the key schedule to help a bit. Could you go to that slide? Yeah, yeah, this one.
Right.
So actually, in Roca is so fast that using nonlinear function is basically as costly as linear. You could actually use the AS round to protect a bit the key. It will maybe not be so slower than this proposal. Would it change anything for your remark, the fact that this would not help so much? So if you were using AS round in L instead, would it make it stronger or not really?
So AS round make it secure, so nonlinear function and but choose carefully to non-free linear functions. So there.
Okay, difficult question.
Sorry.
Okay. Any other questions? Okay, if not, let's thank the speaker and all the speakers of the session.